Thank you, Steve, for introduction part. Today, I'm going to talk about model building strategy. Too much choice can be a bad thing. If you have a data set, you need to fit a regression model to predict something. How are you going to decide which predictor to leave in and which to leave out of it? That's a really important question. Let's look at some guiding principles from my knowledge and experience. I would like to brief 40 steps of model building. Firstly, before going any further, let's be clear about what your model is trying to do. So we need to define an outcome and predictor. So what kind of predictor that you want to put in the model? Predictor which you want to see that which you select based on your reading of the relevant literature or from your experience that you can include in the model. The second step, we have to check the correlation between variables in case that you have many predictors, especially when you study in a behavioral risk factor. You cannot include all because they might affect to your observation. And this can make the confound if you have a lot of predictor in the model. So this step could be quick check to avoid confounding and select some predictor that could be included into the model, and also avoid the multicollinearity problem. And the last step, after we have predictor, we would like to include all predictor into the model. We need to do a Univariate predictor. So we will see which predictor should include into the model. And so it depends on the p-value or the model selection method. The model selection allows you to specify predictor are entered into the analysis. And the next slide, following the last step, there are some commonly used approach for model selection, which most of you already know about that. I will not go into the detail, but from this slide, we have 4 methods that we already know. The first one is a backward elimination. The second one is a forward selection. The third one is a stepwise forward. And the last one is a stepwise forward. In my opinion, I might pick some method that to adjust with my model. So, for example, I will use a backward to entry or predictor and adjust in my way after that. I would like to share some tips with our complicated model selection method in an example. And this is the data. This is the data set about the sexually transmission infection data. This is the cross-sectional study. So there are 189 patients included in the study, and it is just an example. And so there are 6 predictors and 1 outcome. The outcome is a STI. So we say yes or no. Yes, they had a STI, and no, they did not have a STI. And the only one continuous variable is the age. And also 5 predictor is categorical, such as race, sex, amphetamine type use, alcohol use, and lifetime partner. And another 2 we will classify later, and I will explain more detail later. And we will show the mean and min and maximum of each variable, and also the label that define any variable. So before that, we have to classify predictor if from the continuous to categorical. So the first thing, there are common things that we also have a question about that what we should do for continuous variable. We should do as a categorical, or we should do as a continuous. For continuous variable, we can do a model by using predictor as a continuous, but sometimes it's not accurate. As Steve mentioned before, we need to check whether the continuous odd variable show a linear relationship against the probability curve once we do the logic transformation. A common way to do this is to split the variable into quartile, then plot the median of the quartile against the log of the odd ratio, and see if the relationship is linear. I would suggest to use the command lincheck from Stardust to check linearity. This is easy if you use a Stardust to do analysis. So this command helps to check linearity in terms of quartile. If it's linear, we can model the characteristic as a continuous predictor in the model. If not, we have to classify into quartile or clinically relevant category. And the last thing is to collect variable group when the coefficient or odd ratio or hazard ratio is depend on the method, the model that you use was similar between group. You can collect that together. And also maybe you have to check between coefficient and 95% confidence interval that quite similar. You can collect them together. And this table shows the baseline characteristic for all predictor. And I will classify into STI group. And you will see the proportion for having STI and did not have STI. For the gender, you will see that 51% in male has a higher STI than female. And also most of ATS youth and alcohol youth who did not use ATS or alcohol, they has a higher proportion of STI as well. And if you see that in the age group, the younger age has a higher STI as well. And for the lifetime partner, if you see 42% in the last group has a lifetime partner greater than 4, they has a the highest proportion of STI. And you see the correlation among group between STI and predictor. For you will see the rest, there are no significant or there are no different among group of STI in rest. And another variable is set ATS, alcohol, and lifetime partner is correlate with the STI, whereas age is not correlate with STI, from which check with the chi-square test. And for the according, we have age as a continuous odd variable. So we have to do a linearity for this predictor. So the first, we start to make a univariate model. And when we run as a continuous odd, it shows an odd ratio of 0.95, which would mean that for every year increase in age, the risk of having an STI decrease. Before we can model the variable like this, we should accept whether the relationship with the outcome is linear. From the lincheck command, we can get this graph on the right-hand side. And some output that we compare the odd ratio for each age quartile. So in this command, we run the model and classify the age group as a quartile. And the first quartile is the reference group or odd ratio of is 1. And the graph theory shows that the relationship is not linear. And that there isn't a decreasing risk on an STI across all ages. The first 3 quartiles have a higher risk than the fourth quartile. So it should be modeled in quartile, should not be as a continuous odd variable. We should classify into quartile group. And the next slide, we classify age group into the quartile group. For the first group as a reference age from 14 to 19 years as a reference. And also we see the increasing trend of the odd ratio from age 20 to 23 and 24 to 26, that increasing trend and drop and decrease to the in the last group, in the group of age 27 to 45. So that is quite different in the last group. So to make it easy to interpret, so we can change the reference from the first group to the last group. So we will see the last group. We will see the last group as a reference. The odds are always in the same direction, which make the model easier to interpret. So we will see the increasing trend from the first three groups of age to have a risk of STI. So that is make it easy to interpret. And also another variable that when I do univariate model, and we found that for lifetime partner, the lifetime partner normally we have 4 groups. So we see that in the 2 and the 3 and 3, the second and the third group, they are a bit increasing 23% and 27%, and also the 95 confidence interval very close between these groups. So we try to combine this group, and we classify this variable into just only 2 groups. So we classify as a less than 4 lifetime partner and also 4 or greater than 4. We found that lifetime patient who has a lifetime partner equal 4 and greater than 4 had a 2.6 time to be risk of STI when compared with the group less than 4 lifetime partner. So this is more clear and not quite different, and probability chi-square p-value overall still significant. And this table shows univariate model for all predictors. People commonly build multivariate model by including terms from the univariate model that have a p-value is less than 0.1. This is because they show some association and it could be potential confounder. Another way would be to select a higher cutoff or include things in the model which you have an association with the outcome to adjust for them. So when you look at the in each variable, we see that for rest there is not significant if we would like to entry at 0.1. So this can include into the model. And also for sex, we will see that sex, ATS use, alcohol use, and lifetime partner, that's still less than 0.1 if we would like to include in the multivariate model. But it cannot include into the multivariate model because it's over 0.1. But when we dig to interpret for each variable, for example, we will see that male will have a higher risk of STI at 2.2 times when compared with female, and ATS use. Patients who use ATS were more likely to have STI about 3.4 times or on. And also for the age group, there are increasing trend of odd, but it's not significant at p-value less than 0.1. So the first step, we will not include this into the model. If we would like to include two multivariate model at p-value is less than 0.1. In the first multivariate model that we include only when p-value less than 0.1. We will see that less variable is significant with the STI. Previously is not significant with the STI when we did a univariate model. And if we look at the sex, ATS, alcohol, and lifetime partner, they are still significant with STI. And when we interpret for the sex, After adjust for all predictor with univariate p-value less than 0.1, we found that male had increased risk to 2.7 times higher odds of STI when compared with female. And also, patients who use ATS were more likely to have STI. Increased odds to 4.2 times with wide confidence interval, because we will see that they have a small proportion in patients who use ATS and they have having STI. So they make the confidence 95% confidence interval is wide. And this can be a great model. But for the another option that I want to show you is, I would like to include it into the model, because I believe that age might affect to STI through confounding. We found that there were no different direction of odds ratio after adding age. There were some slight change of odds ratio, such as increase in odds of 2.8 in male, and decrease in odds for the ATS use to 3.8, and rest still significant when included with another variable in the model, and also the right time partner. So even we add it in all these models, so another predictor still is significant with STI. So it depends on what you want. So according to this model, I will conclude the final model as like this. Normally, if you want to show the final model, you should show the univariate model compared with the multivariate model together in the same table, so that you will consider how different from the univariate model to the multivariate model. And if you see that they are still the same direction from the univariate model when they include into the multivariate model, such as the gender, such as the sex, and we will see that male has increased risk to 2.8 times higher risk of STI when compared with female. So from the univariate, just odds ratio for gender just only 2, but for when include to the multivariate model, it increased to 2.8 times, and for the ATS use, so it's around 3.9 times when compared with the patient who did not use ATS. So increased from 3.4 to 3.9 in the multivariate model with another variable. And also the lifetime partner, you will see, but it's a bit decreased from 2.7 to 2.4. So, but the thing that is still the same direction. So, and this is a model that I would like to conclude. So you can build your own model based on what you want to present. It should be reasonable and realistic. And this model that I like it. Thank you.